Framebuffers, vectors, bitmaps, bit depth, fonts, rasterization. All these terms relate to computer graphics. You've probably heard at least some of them around on the internet somewhere. They are seriously cool. Computer graphics is such a mystifying and interesting field. How do things actually get drawn on screens for people to visualize? We're going to write our very own simple display driver for this embedded systems display right here. I'll pop it up on screen to illustrate all of these concepts, because computer graphics, such a cool field. These are baseline concepts and they scale up pretty complexly. So complexly, is that even a word? Anyway, we're going to write a very simple display driver to get you in the headspace of all of these concepts, illustrate them, and hopefully get you interested in computer graphics. What you see before you is a simple smiley face rendered on the display. How did we even get that far? How did we tell the computer we want to put a smiley face in that exact position on the display? How do we even represent the smiley face in computer language in the first place? We're going to get into all of that with first an example on Framebuffers, which answers our first question. Don't worry, we'll dive into the code straight after this. I know the whiteboard and the graphics are a little bit boring, but bear with me, okay? So a Framebuffer is simply the in-memory representation of the output image on the display. So let's say I want to render this smiley face here. In memory, I actually have to store that. So what my computer will do, either the CPU, depending on the system, you might have a GPU in there, what it will do is execute the instructions necessary to construct an in-memory representation of your output image. So this is where the concept of bit depth comes in. So what is a frame buffer? The most simple frame buffer you can have is simply a one-dimensional array. That's it. Like down here, for instance, we have this one-dimensional array, which will simply be every byte is a pixel, and it is the width times the height. Now, think about this. This is the concept of bit depth. Bit depth, and you've probably seen this in your, NVIDIA or AMD control settings panel, is how many bits are able to represent every color. So think about that, right? If we have a 1-bit frame buffer, that means that every pixel on the screen has one single bit available to describe the color. Essentially, that's a 1 or a 0. This is known as a mono frame buffer. So if you've ever seen, I'll flash these images up on screen, everybody's probably seen the blue and white embedded displays. That would be an example of a mono frame buffer, right? You might have a 1 represent a white tile and a 0 represent a blue tile. And there's also this particular display that we're going to be writing the driver for. This uses a mono frame buffer. It's an e-ink display where a 1 might represent a white tile and a 0 might represent a black tile. So mono is not necessarily blue and white or black and white. Mono really just refers to you have 1 bit available, and those colors could be anything. I could have a red base and a green, set, and that would still count as a mono frame buffer because I'm still using 1 bit of color to describe the image on the display. Now, if you want to draw more color on the screen, all right, well, you can talk about 24-bit, you can talk about 16-bit. There are all of these color representations that you can have, and they are all designated. So RGB 888, for instance, is 24-bit, RGB 565 is 16-bit, etc., etc. And if you think about what that means, I'll scroll down to a 24-bit example here. Essentially, you can still have the same representation in memory, but you are multiplying this by your bit depth. So we'll dive into what that actually means. But I want you to first consider a mono frame buffer. So with this mono frame buffer, what we have is every single pixel on this display can be represented by 1 bit. So even though down here, I have this array filled with bytes, because in C, that is sort of the minimum that you can specify in terms of arrays and such, you would still, to save space, only represent everything by a single bit. But for the sake of simplicity, we are going to say that every pixel in this display, and by the way, this is a 34 by 16 display, I know, ultra high resolution. We're going to say that every pixel is represented by a byte just to keep our calculations simple. So let's say I want to render this smiley face here on the screen. I know it's a fantastic drawing. Let's think about that for a minute. So our start pixel, if we think about this in terms of an array, okay, we're going to use a one-dimensional array. The question is, can you use more complex data structures like multiple dimension arrays? The answer is yes, you can. We have this start position here is 0. This is our initial index, which would be 0. And we can go all the way along until we get to here. and maybe you can't see because my beautiful face is in the way, but this is a 33 over here. So this is index 33. And so that means that we start at index 0, we're at index 33 right now, and because we have a one-dimensional array, when we wrap all the way back here and start at index 34, like this new line starts at index 34. So if I want to access the pixel 73 on our 2D coordinate system, that would represent the start of the smiley face here, I could use the formula x plus width times y to get the index of that. The index of the bit, if we're using a normal mono frame buffer where every bit represents a pixel, or for our simplified example, 109 as the index for our array where we want to flip that. So let's just say for the sake of argument that this right here was index 109. What we'd actually go ahead and do is flip this to a 1. So we draw it as, 1, 0, 0, 1, etc. We're going to write some code to do some very baseline mono frame buffer operations. Now keep in mind this code is being written to be illustrative and not efficient. There are optimizations that you can do to the code we're going to be writing today. The first thing that you want to go ahead and do is make yourself a .c file and a .h file like I've done here. I'm calling mine Baby Driver. It's a little film you might have heard of. And the first thing that we're going to want to do is define the frame buffer object itself. So that includes the width and the height of this display, which you can get from the datasheet or however else you're finding information about your physical display. So how many pixels can it actually represent? And that is going to form the size of our frame buffer. Something I want to make clear before we begin is that the graphics library we're making implements software rendering. What that means is that graphics operations are done using the CPU rather than the GPU. I think this is still valuable for newcomers and beginners because if you've never done any graphics programming before, the flow of operations will make complete sense to you and you can use that to learn the concepts and then you can apply them to GPUs where it makes a little bit less sense. Plus, if you're into embedded systems at all, a lot of the rendering is still done in software using microcontrollers directly, even really advanced graphics. Here's the datasheet for our display. As you can see, we've got a display format here of 122 by 250. I'm going to generalize this to 250 by 128, so it's nicely divisible by 8 for us. And I'd recommend you do the same if you're working with mono frame buffers because we'll be representing this in bits instead of bytes. And here's our frame buffer size definition. So of course, it's just going to be the frame buffer width, which we've defined here as 250, height 128, and this times this divided by 8, because remember we're going to be working with bits. So every bit in our mono frame buffer is representing 1 pixel on the display. Let's define our frame buffer. So it's going to be a uint8t one-dimensional array. I'm going to call this BD frame buffer. It's going to be BD FB size, and we'll initialize it all to 0. And of course I have to include standard ints. So this is going to be the frame buffer object in memory that we actually do operations on and set pixels and unset pixels. We're going to write the very fundamental operation for our frame buffer, which is to set or unset a pixel. Going to start off like this. We're going to call this void bd set pixel. So you can see here we've got an x, a y, and a state. So remember we've got a mono frame buffer, so it'll be set, which I'll do as true, or unset, which is false. If you guys forget about bits for a second and imagine this 1D array as an array of bytes like we were doing in the theory overview section, then this position here actually lands us on the byte that we want to flip. So if you think about it, that's the width times y. So, we're going y down in terms of our rows, and the rows are of this width, plus the x. So we go down in the y direction, and then plus however many x that we want to go to. And so this will give us the bytes. Now, what we actually have to do is go ahead and divide this by 8, because if you think about it, what we've done is actually overshot by 8 times because there are 8 bits in a byte. So if we want to find the correct bit to index, then we'll land on this position here when we divide by 8. A cheeky optimization you can do is to change that divide by 8 to this bit shift by 3, because this will give you the exact same effect as a divide by 8 if you consider the bit maths, and on some embedded platforms they don't actually have hardware division, so division operators with the traditional division will be very slow. Now, the compiler may or may not do this for you, but it's fun to see it written out because it's interesting, and yeah, hardware division, you want to have it, otherwise your division is going to be very slow. Now that we've landed on the correct byte, we actually have to set the correct bit because we've just landed on the one that contains the bit that we're looking for, but we haven't actually set that yet. So if you think about it, this is just going to be a very simple bit mask. Now, here is where we actually do that depending on the state. So we've got if state, and here we're going to OR equals this, so we're going to be setting that to a 1, And down here, we're going to be and equaling the not of that. So that'll be clearing that bit or setting it to a 0. Now you might be wondering, Hoff, I understand bit masking, but what is up with this maths over here? What's going on there? So we'll explain that very briefly. 0x80 is actually the representation of 128, which in bits is 1 followed by 7 zeros. So that is actually the mask that we're going to want to move. What we're going to be doing is shifting the position of that 1 to highlight the bit that we want to set. And we do that by shifting this by x ANDed with 0x7. So I'll put this 0x80 up on screen. What this 0x7 actually is 1, 1, 1 in binary. And what that's actually doing is capping this x value for the shift such that our shift is not going to go out of range. And trust me, this math just works. If you think about it, and I'll put this stuff up on screen, you'll see how this works. We are shifting this by this x position, which gets capped at 7. We can also do an equivalent getPixel function like this because there are many situations where you would want to know the value of a pixel in your frame buffer, whether it's set or not. And we can do this in functionally the exact same way. We calculate the position here, but instead of setting it with the bit mask, we're actually just going to return the value of the bit mask. So if it ends with our mask, we'll get a value greater than 0, or we'll get 0 if it does not. And that's kind of how our mono frame buffer is working. And we can apply this to our 24-bit one. So let's say down here, we're looking to store 24-bit color. So that means we have 8 bits available to us to describe the pixels. And you might have realized 8-bit color is actually what traditional hexadecimal web-based colors use. Like if you've seen these HTML codes and you'll see 255, 255, 255, you know, this is actually an 8-bit color representation here, this web-based hexadecimal code. And 24-bit color is the most common on modern monitors and such like this. So we could describe a 24-bit frame buffer like this. We could still use our simple 1D array. Could you use a more complex data structure? Yes. For the sake of simplicity, we will not be doing that. So we have this one-dimensional array, and the size in bits, keep in mind this is the size in bits, is now going to be width times height times bit depth. So that would be, for our display here, we have a 34. So this would be 34 times 16 times 24. And you can add that to this formula here to find the bit that you want to address. So if we still wanted to access this position here at 7.3, to land on the sequence of bits that we need to change, because remember, in here, we've gone from having 1 byte representing an individual pixel to now what we would actually have is a group of bytes that represent 1 pixel. So over here, we would have like a red, over here we'd have a green, and here we'd have a blue. So you can see now that instead of just going from a mono frame buffer where we have 1 byte or 1 bit to describe our color, we can now use a group of bytes. In this case, for RGB 888, we have 1 byte that describes each RG and B. So our formula is now going to have this bit depth at the end. So if we want to index 7.3, we can plug 7 in as x plus our width, which is 34. This should be a 4. 34 times y, which is 3, times our bit depth, which is 24. Now, consider that we're looking for the index. So, you know, we've got these indexes here. So divide that by 8, and we get 327 as the index in our, you know, grouped array that we start at. So, you know, for the sake of argument, let's say this was index, I think it was 327. So this is index 327. For that particular pixel, this is going to be the R, this is going to be the G, and this is going to be the B. So that is a very simple overview of the concept of a frame buffer, how you might store one in memory, and bit depth. While we're on the subject of frames and frame buffers, I want to talk about refresh rate and frame rate. Now, these are very popular terms with gamers, of course, because these two things as a sort of coupled pair, if you like, determine how smooth or fluid any animations, graphics, video playback look to the person experiencing them. Now, refresh rate, you can think of it as the hard cap, and this is measured in hertz. In terms of frame buffers, this is the number of times per second that we can push a frame buffer update to the display. So if I have a refresh rate of 60 Hz, which is a very common desktop computer display refresh rate, That means I can push a frame buffer update to that display 60 times per second, and it will actually properly update on the display. If I have 144 Hz and I'm running 144 Hz at my house, that means I can push a frame buffer update 144 times per second. Now, on this e-ink display that we're going to be writing the driver for, I was able to achieve a refresh rate of 1 Hz, which sounds crazy great, right? Crazy, crazy, crazy. But for an e-ink display, 1 Hz is not actually so bad, and I was able to do that without very much effort. Now, frame rate is sort of like the rendering cap. So if you think about your hardware compute power, whether that be on the CPU or the GPU, we talk about rendering, we talk about preparing or rasterizing the frame buffer, all of these sorts of words. Essentially, as we mentioned before, the frame buffer is the image representation or the in-memory representation of the image that's displayed on the screen, the complete image. And to do that, you have to run a whole bunch of calculations, like you are rendering vectors to the screen, you might be doing 3D rotations and things like that, that if you're doing a much more complex graphics driver, you have to deal with. And if your compute renderer falls behind your refresh rate, like you've got a time operation going tick, 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 we're pushing a new update, that's when you get lag, screen tearing, things like that. So you want to make sure that your hardware is more performant. If you're running an embedded system, you want to make sure that your CPU, and I think some STM microprocessors have 3D accelerators or 2D accelerators anyway, but you want to make sure that your hardware is up to scratch and your algorithms are optimized. Those are the two big things. Bits, bits, bits. I hope you guys like bits. We're going to talk about bitmaps. You've heard the term bitmap. Everybody's heard the term bitmap. What is a bitmap? A bitmap is referred to with images, okay? So let's say we have this image, and this is a fantastic website. I'm going to link this in the description. This is a great website. So a bitmap, if I were to represent my image, this is a bitmap, okay? What we were just looking at before. If I take this little guy outside of this display, and I just have it as like, let's say I bound it here, I bound it here, I bound it here, and I save this as an image, that's a bitmap right there. A bitmap is very simply an array or otherwise storage of bits such that, this one's a 0, this one's a 0, this one's a 0, this one's a 0, this one's a 1. That's what a bitmap is. A bitmap is simply the in-memory representation of your image. It's almost like a mini frame buffer in of itself. So let's get back to this website where I'm going to show you this in a real image. So this is really great. You can upload an image of your choice and you can essentially choose all of these things about it, and you can turn the palette on to whatever you want. So these were some of the ones that I was talking about before. We have 1-bit line art, which is mono, our mono frame buffer. We have 8-bit, where's our 24-bit? Yeah, so 3 bytes per pixel. This is our 24-bit RGB. There's also RGBA, if you guys also know that you could essentially add an alpha channel for transparency and such like this. But yeah, so if we just go ahead and hit convert on this, and there are some other things you can change as well. So you can make it static, const, unsigned. You can change this to a different data format, a progmem. If you're just storing this in a normal C program, like progmems for embedded and stuff like that. Anyway, this is our representation of the image. This is a 704 by 704 image, and it gives you a preview of what it'll look like on the display in your format. And what we're actually going to do is render this to our little display that I told you we're writing a driver for very shortly. So essentially, yeah, if you want to render a bitmap, think about this. This is a massive, massive thing to know. If you want to render a bitmap, all you need to do is directly copy it into the frame buffer. Because if you think about it, this is essentially already in the perfect frame buffer output form. We simply have to copy it to the frame buffer and then send that off to the display driver in order to actually render that on the screen. So if I change this to 24-bit RGB, you can see we've got OXFFF, and this is what I was talking about before. So each of these will be able to represent 8 pixels because we've got 8 bits on our mono frame buffer. If I go ahead and hit convert on this, you can see here we now change to hexadecimal codes where each of these lines here represents 1 pixel because we've got all of these hex codes, and we've got 8 bits per color. I resized that image so it will actually fit on our screen, and I copied the bitmap representation from that website into this kuromi.c file, and I also have this header file, and all this header file does is define the size and let us use this array in our other programs. So what we're going to do now is write a function that takes a bitmap, with an X, a Y, and a size, and just copies it into our frame buffer. And of course, you can stack bitmaps on top of each other, and that's how you would create a more complex scene if you like. We're going to write a function to copy this bitmap into the frame buffer. Now remember, this is not the most efficient code, this is the most illustrative code. So we're going to start off by taking in an X and Y. This is going to be our start position. We're going to take the width of the bitmap in bits, the height of the bitmap in bits or pixels, and the bitmap image itself. Now the reason we're doing this all in bits or in pixels is so that to the person using this API, it's the most transparent, right? Like we want to be able to have them access it in X and Y coordinates and in pixels, rather than having to worry about the individual bytes or such how we're representing our frame buffer. So it's just a kind of abstraction. And because we have these get and set pixels, we're perfectly able to do that. The basic idea is that we're going to loop through every single bit in this bitmap and set the equivalent position in the frame buffer. Now to do that, we're going to need this mask in order to actually check the individual bit of our bitmap. We're going to need the total size of this image that we're going to loop through. This is in bytes. So we're going to be looping through this array in bytes and then looping through each individual bit of individual byte. We're going to need the original X and Y positions that we start at because we're going to be modifying these as offsets, and we're going to be looping through this entire array in bytes because again, bytes, that's the most minimal that C can represent for our indexing. This is how we actually set each individual pixel or individual bit in our frame buffer according to the mask. So we're going through and looping through every bit because remember, we're looping through every byte. Now we've got to loop through every bit. This check mask is just going to go 1, 1, 1, 1, 1, so that we can check the set value of each bit over here in our bitmap. So then all we do here is set the X and Y position to the state of this bit mask, because remember, if this turns up true or like positive, so if there's a match between the 1 position and one of the bits in here, this will evaluate to greater than 1, which is true, which is the, the Boolean state for this, or otherwise that will equivalent to 0, which is going to be false. So this will get set to a 0 in our frame buffer. So that's essentially what we do. And then we go X++ because of course we're going 1 bit at a time. Now, keep in mind, we're not done yet, because what you might notice is because we're dealing with one-dimensional arrays here, what this will actually do is set this in landscape mode forever, and we never break to a new line, even though we might have reached our height requirement. So what we're going to have to do is add a check to increase our Y position, which I've gone ahead and done here. So here we check if X minus the original X, because remember, we don't necessarily start at X equals 0. We might be starting at like X equals 50 or something like that. So if the incremented X, so this will be like 51, 52, 53, blah, 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 blah. If X minus the original X is equal to the width, so that means we have essentially gone widthways the entire width of our image. Then we're going to increase Y, and we're going to reset X to the original X position. Because remember, like if we're setting X back to 0 and we've started our image at 50, we're going to draw the first line at 50 and then the rest at 0. And we don't want to do that. We want to reset to the correct X position. So that's why we're doing this. And also if our Y position is equal to the height, then we're just going to return, because that means we've finished the height of our image. Great, now I can show you guys a fun demo. So what I've done here is I've just included all of the things, and we're going to draw the bitmap, and then I'm going to print out the frame buffer that we've created, so you can see, just using standard IO for now. So what we do is we just draw the bitmap here. I'm drawing it at 50. Then we loop through the height and the width, and all I'm doing is just getting the pixel at that position and printing out what it is. So let's go ahead and check this out. If we go here and I do the whole make thing, boom, we print out our frame buffer, and you can see we're printing this little image out here at 50. So now what I can do is if I want to modify this, like let's put this at 20, I can go ahead and do that, and you can see we're drawing it at 20. So we are actually updating. I can go ahead and draw 2 of them. So if I want to draw another one at, like 60 or something like that, I can go ahead and do that. And so, it's actually gone and overlapped it because I haven't put them 100 spacing apart. But if I do this one at 120, it should be spacing them apart like that. And my terminal is going off the screen, unfortunately, because, I don't have enough room to show the whole frame buffer, but that is what we're doing. So you can see that we're literally, and I can maybe draw another one at a different Y position. So if I position them in between here, 60 at Y, like 40 or something. So we segfaulted just there, and the reason for that was because I forgot to add this check here to not go out of bounds. So, sorry guys, my bad, I forgot the out of bounds check, but we are no longer segfaulting. In fact, what I can show you is this, which is the, overlapped and cut off third image that we're pasting here. And just like before, here is our fully rendered scene on the display. We've got the 3 overlapping images here, just like our virtual frame buffer, except this time we've pushed it to the actual display. Pretty cool, huh? Everybody loves vector graphics these days. You go to the web, you download an image, it's sometimes an SVG. They're great for icons, they're great for scaling. What is a vector image and why is it different from a bitmap image? Well, think about a bitmap image. In your image file or in your memory, you have stored pixel information for every single pixel, and you can get compression formats like JPEG that do compression on these and try and reduce the file size. But if you consider the simple bitmap that we were talking about before, you have a representation of every pixel in the file or the computer's memory. And that actually does take quite a bit of storage. Now, they're fast to render because all you have to do is pretty much direct copy them to the frame buffer, but they take up storage, and sometimes you don't want that, especially for more simple graphics. Now, we're here in Inkscape. This is a very popular vector graphics editor. I have no idea how to use it. I've just drawn this little smiley face here. But vector graphics, the key thing that makes them different is that instead of storing pixel information, they store instructions on how the computer can actually draw this in real time. So if I were to save this smiley face, instead of saying, oh, we've got a pixel here, pixel here, pixel here, it would actually save it as instructions on how to draw. This is a KDE SVG file. It's actually the one for the file manager Dolphin, which let me see if I can get up a very, very small example of. Maybe you've seen this if you're a KDE user. But essentially, yeah, the instructions on how to draw this are a little bit complicated, and on an embedded system, good luck drawing this as a vector. So yeah, use your vectors according to the system that you're scaling for. If you think about the most simple vector graphic that you could draw, it's probably a rectangle or a box. So here we've got the instructions to tell the computer how to draw this, because again, that's what a vector graphic is. We start with X and Y, so our start X and start Y. We've got a width and we've got a height. So this is literally just one of the most simple vector graphics. We loop from X, I equals X, I less than X plus width. So we start at our X and we just go along the width. And we do the exact same thing for the Y going down. We just have a simple bounds check here, remember the previous section, and we set the pixel if that bounds check is correct. So I've added this into our test code that I can show you. So here we draw the bitmap, right? And then down here we draw our rectangle at x40, y105 with a width of 50 and a height of 20. So if I switch on over to that, you can see here, this is what I drew, right? So if I show you it running again, this is like this. Now keep in mind, this is a monospace font, but the height isn't exactly accurate. So if I draw a square, like if I change this to 20, it's not actually going to look like a square on here because the height is different, but this is actually 20 pixels down and 20 pixels across. So if the pixels were a perfect square like they will be on the display, this is a perfect square. Well, trust me on that one. Trust me on that one. So yeah, we can add another one to show you guys, right? So, if I draw this at 0 instead, then you can see we're just drawing 2 of them. And you can see here that we're now starting to be able to construct our frames. So in our scene, if I want to have this bitmap down here and this rectangle down here and, have another one over there and blah, 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 this is how we construct our scene or our frame that we want to output to the user. And if we have animations, all we do is we update these little things here on our frame buffer according to, what tick we're up to. Also, in our exploration on vector graphics, I've done the world's worst triangle algorithm. So here we can draw a right diagonal line. So that's a diagonal line going right and up. So if you think about that, you start off at the Y position, you go Y plus height, and essentially you add an offset. So every time you go across by the width, you add an offset to the next line. And so if we start here originally and we go like that, the next line, we're going to start here and go like that, depending on your offset. So that's how you draw a diagonal line. You essentially draw a straight line, adding an offset every time. And I did the same thing for a left one, where we take away the offset every time. So our triangle algorithm is you draw the right diagonal, you draw the left diagonal, and then you draw a rectangle as the base. World's worst triangle algorithm, and I've got it in here in our little scene. So if I swap over to our frame buffer, You can see I've drawn a little triangle in there, and we can modify some of the parameters about this triangle. So let's change the side lengths to 10. Let's change the position to like 40. And you can see we're drawing our triangle. I can draw actually I might not draw the 41 because that'll overlap, but I can draw our rectangle, I can draw our triangle, I can draw our bitmap. So this is vector graphics, right? We're giving the computer instructions on how to draw our scene. And here is our vector graphics scene drawn on the display. So we've got a bitmap over there on the left, and then our 2 vector triangles and our vector square. So essentially, once they're in the frame buffer, vector graphics rendering works exactly the same way as normal bitmaps. They just go and get transmitted to the display. Just drawing the vector graphics versus drawing bitmaps is where you get that big difference. We're going to talk about fonts. We've learned about bitmaps, vectors. How do we draw text and fonts on the screen? So if I want to draw like the quick brown fox jumped over the lazy dog or something like that, how do I actually draw that on the screen? Like when we're using this, it's pretty standard to draw text on, normal computer programs. Like we're going to have printf that we can use. But what if I want to make a printf equivalent that goes directly to the screen? So this is where we need to talk about fonts. Now, in the embedded world at least, there are vector fonts and bitmap fonts. Now, in the real world, we use TrueType and OTF, OpenType fonts, which are not exactly vector and not exactly bitmap. They're sort of a hybrid between the two. I'm not going to pretend to really understand the innards of OpenType and TrueType fonts, but they are something in between. We're going to deal with the more simple pure vector versus pure bitmap fonts. Now, here we have a bitmap font generator. This is another excellent website that I will link to you guys, where we can really see how bitmap fonts work. We know about bitmap images. I want you to think about this. A bitmap font is nothing but a collection of bitmap images that represent the entire alphabet. So A will be a bitmap, B will be a bitmap, C will be a bitmap. And so all you have to do in your code is if you can map each individual character in the string, so you're looping through the string, all you have to do is link that to the appropriate bitmap and draw that bitmap using the exact same logic as we've already done before. So have a look at this website, right? We can select a font down here, which is really nice, and it will generate the bitmap code for us, which is, this thing here. And so what we have to do is go through and we index this array over here. We index this array at where the character we want to draw is represented. And that way we can draw the text on the screen exactly like this. There are different families that you can choose. So, you can go ahead and choose a different text family if you're wanting a different font style. And you can even, you can make your own font styles if you like and convert them to bitmaps. There are bitmap, image to bitmap generators, and you can go through if you've got a font that you want to convert like Arial or something like that. We're going to use this website to generate ourselves a bitmap font. So a couple of things I want to clue you guys into. You go over here to presets, go ahead and select generic C8x8, and then go to the output and select C array flat, and go and select yourself a font. So I actually want to use IBM CGA 16x16. So it'll tell you the pixel size, the width, and the spacing, and that is depending on your screen size. 16 size font is what I want to use for today. And you can change the width of the output and the height of the output, and you can see what your bitmap font is going to look like in real time right here. If you still get out of range errors when you've put in the correct width and height, you can add in an offset, and there we go. We've got our flat array of bitmap fonts. So this generates a bitmap image for every character in the alphabet, or well, you can select the range here. But anyway, we're going to use this website to generate ourselves a bitmap font. So a couple things you want to do: go to presets, select generic C8x8, and then come over to output and select C array flat. That's what I prefer to work with. You can choose nested if you prefer, but our calculations we use a flat array. Then choose yourself a font. I actually want to go with the IBM CGA family, and I'm going for a 16x16 font size. Choose that depending on the resolution and size of your display. For our case today, 16x16 is what I want. So go ahead and change the width to 16 and the height to 16. And if it's still cut off a little bit, I'm going to add a tiny little Y offset. So this is a flat array of a bitmap of every single character of the alphabet. So what I want to go ahead and do now is hit MSB first. This is a question of endianness. So endianness is important for bits and bytes and how bytes are represented in different computer systems. Today, I'm not going to really talk about it because that's not the focus of this video, but it's an interesting concept and I might do a follow-up later. But anyway, this is a representation of every character in the alphabet in bitmap form. So go ahead and copy this into a C file and we'll get writing this algorithm. Now to actually write the text drawing function, remember what I was telling you before? It's literally, these are all bitmaps. So we can use this same draw bitmap function. We just have to map the character of the text to the correct bitmap. To start us off with this prototype, we've got the start X and Y, the size of our font in pixels, so that'd be 16 for us, and the text that we want to draw. To start off with, we've got the font that we want to go for. So oftentimes, if you're doing a graphics library, you'll have multiple fonts and multiple different sizes, and they're all these flat arrays. So what you can do is just swap this pointer depending on, for example, the size parameter that's passed in, and choose a different font from there, or otherwise do it. So this is just a pointer to the font that we want to use. This is a pointer to the character that we want to use, and we'll be using some pointer arithmetic in order to get that. We want to keep the starting X and the starting Y, like the running X and the running Y, because what we're going to be doing is text wrapping. So, if we get to the end of the display, we want to wrap the text over at the beginning. So we need to keep track of a running X and a running Y. And the target is going to be used for our pointer arithmetic to get the character that we want. So we'll write out a switch statement for the size, which we've just done like this, right? So in this case, if we wanted a different font size, like, if we had a case 24 with a different one, we could maybe do like font equals CGA 24 if I had one. So you can just use this switch statement sort of prototype to change the font that you want to use or target. Then we just want to loop through every character in our text, which we start off pretty standardly like this. We go from I to the length of the text. And now we do the math that we need to target the right pointer. So what is this? Size times size divided by 8. If you think about that, we're just taking the full size in memory of our character, which would be 16 pixels. So 16 squared because it's a square. And then we divide that by 8 because we're doing this in bits. So this is the size of our characters in memory. And what we actually do is multiply that by the character that we're at minus a space. Why do we do that? I'm going to put an ASCII chart up on the screen. So the ASCII spacebar is the first starting character in our ASCII alphabet that we have bitmaps in order to represent. So if we take the value of our character, which will be after the spacebar, and we minus the spacebar away, what we actually are left with is how many spaces in memory, like how many characters in memory of this big flat 1D array we need to increase by, or increase our pointer by, in order to land on the target that we want, which is the character of this text, which we can write as simply draw car is font plus target. So that's our pointer arithmetic there. Hopefully that makes sense to you. All we're doing is finding out how many characters in memory we need to skip in order to land on the target that we want. From here, we can literally just call this draw bitmap function, because that's what we're doing, right? We're literally just drawing a bitmap now that we found out which character we want to do. And the width and the height are obviously going to be our font size, which is usually, 16. And now because we're going character by character, we have to increment running X by the size. So that'll move us along in our frame buffer to the next point where we're going to draw this character by the width of our character. We're not done yet though, because we still have to do some boundary checks. So for example, what do we do if we overrun our width of the display? So we're drawing our characters and we get to the edge of the display. Well, what we're going to do is reset running X to X. So if you think about that, if we go to a new line, we're going to start back from where our text started, and we're going to increment running Y by size. So down here, after we finish drawing a character, that's where running X is incremented by the size. But if we hit this, the end of the display, and we want to go to a new line, that's where we increment running Y by size. So what we're doing is just jumping back to that original position, one line down. And I'm also going to add a boundary check for the Y, because if we've reached the end of our display, we just don't want to render anything. And that's all there is to it. So over here on our test program, I'm going to draw the text https trent.surf. Big things happening, watch this space. CSGO surf is so back. Anyway, if I go over to our little thing over here and I run this, you can see in our virtual frame buffer, we've printed out the text https trent.surf. And I can of course modify the position of this. So, if I want to kick this back up to y equals 40, I can go ahead and do that and bring it back down. We rerun this, it goes up here. So yeah, let's see this render on a real display. Here's text from our library rendering on the real display. Now you might have noticed that the color is off compared to our background. Well, if you've thought about this at all, inverting the color is actually really trivial. All you have to do is whenever you see a 0, write a 1 instead, and whenever you see a 1, write a 0 instead. So you just invert it if you want to invert the color. So the color not matching here is pretty trivial to fix. The big thing is that we have the text drawing in the first place. We have our in-memory representation of our frame buffer. We can draw vectors, bitmaps, fonts. How do we get that thing onto a real display so it's not just all in memory? This is where it gets a little bit device specific. So in these little embedded systems displays, they're actually made up of two main components. Well, a couple main components. But on this display here, you'll have a controller chip that actually is the thing that handles communications. So when my microcontroller wants to render a frame buffer update or do whatever it wants to, it will be talking to the display controller, and the display controller will then apply the physical characteristics, the physical electrical characteristics required in order to update the pixels and get the pixels on the display to change. So you have two components that are typically mixed and matched that you need to consider when you're writing a driver for these, which is number one is the controller. So what is the control protocol that you actually have to speak? What's the language you have to speak to this thing to get it to do what you want? And particularly with these e-ink displays, the physical characteristics of the panel, which is the second component, you've got the controller and the panel, that's really important as well. Now, this particular display communicates using SPI. Now, if you're not familiar with SPI, I did a full video where I do the most common embedded systems protocols, which are I2C, UART, and SPI. If you're not familiar with SPI, check that out. SPI is the communication bus that we're going to be using to speak the protocol on this thing, which we'll understand from manufacturer-provided code and the datasheet. We have here the two files of interest. On the left-hand side is the manufacturer-provided code. You can see we've got a 122 by 250 display using this IC with 4-line serial on 3.3 volts, which is exactly the panel that we're targeting. And on the right-hand side, we have the display controller datasheet. Now, what we want to do is sort of match the operations that are happening in this file over here with the manufacturer provided code to what is happening in the datasheet. Because here's the thing, guys. This code sucks, this manufacturer provided code. It's horrible. Look at this. Look at how poorly this is formatted. It's doing all sorts of very weird things that I don't want anywhere near my embedded code bases. So what I want to do, and look at this, they haven't even bothered to do hash defines for the commands and the data that they're sending. So what I want to do is, like look at this. Who wants to use this code? So what we're going to do is sort of use this and this datasheet to write our own communication library to talk to the display that hopefully is done a little bit like, what are they do? What is this here? How is that gonna work into any embedded code base ever? Yeah, so what it looks like they're doing over here, by the way, is they have these full frame buffer images, right? So they've got this full frame buffer representation here, and they just go ahead and transmit the whole thing. And that's what they do. So there's no graphics library in here like what we've built. This is literally just, we've got a pre-made frame buffer and we're going to transmit it to the display, which actually is fine because we've already got our own graphics library. What we want to do is take the communications part of this, which is, you know, this section here, right? We've got the reset, we've got the init, we've got the clean display, we've got pick display, and we just want to make our own that's written a bit nicer, and then we can sort of tie that together with our graphics library, and we've got a full display driver for this device. Now, the way that you approach a task like this is we're going to start at the start. And at the start, we call EPD reset and EPD init. EPD init sounds a bit more interesting, so we're going to start with that. As you can see here, it's got a couple flags that it sets up, so that might be useful for us later. We're kind of just going to do a nicer logic put. We're going to see if we can reorganize this logic and make it a bit nicer. And also, I want to do definitions for all of these commands, because, like, you know, this doesn't mean anything to me if I'm looking at it. So what we can do is cross-reference that with the datasheet. So we can see write command 0x00. What does it actually do? Well, let's find out. If we scroll down on the datasheet for the control chip for a little bit, we'll eventually land on this command table. So what we'll actually find out is that the command, which is all zeros, 00000, is this panel setting command here. And if you scroll down a little bit further, it'll actually give you information on all of the things that this lets us do. So as you can see here, if CD, by the way, for this display, this is one of the quirks of this controller. If you set the CD line to 0, you are sending it a command. And if you set it to 1, you are sending it data. So that's the kind of distinction that it makes. That's another GPIO line that you would set as opposed to, you know, chip select and everything like that. So this is the command line here. So for 00000, that is this panel setting. So what you would then go ahead and do, if I go to our thing over here, you do exactly what I've done. So I'm just going to hash define BD command PSR as 0x00. So that way we can now go over to, this init function or wherever, if we write our own init function, instead of saying, transmit command 0x00, I can then say transmit command compsr, which makes a lot more sense. I've gone ahead and done just that. All I did, this looks scary, like, oh, what are all these hash defines? Literally, it's just me going through this command table. You can see here, power setting, PWR, is 00000 blah 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 1. So, that's what I've set it as here, 0x01. And this is how you approach something like this, guys. It's grunt work, you just got to do it out. We go through, now what's the next command we do? Power off, that sounds useful. Maybe I do want to send a power off command. Well, that's 0000010, so that's going to be command OX02. So that when we're actually using it in our display driver, it makes a lot more sense. It's more normal than saying, if I've got a command that I want to turn it off, if I just say transmit command OX02, that means nothing to me when I'm reading it, and it means nothing to anybody else using the library. So this is just a way to make it a lot more readable and a lot more usable than whatever they're doing here. We can do the exact same thing for the data passed to all of these commands. So you can see here, as an example, we write a command, OX01, and then we write data. So what does all of this actually mean? Well, the datasheet is going to tell us that. So for this power setting here, you can see CD flips from 0 to 1, which means we're no longer sending a command, we're sending data. And you can see here that the first byte is going to be this VSEN and VGEN. So what does that actually mean? That is the source power selection and the gate power selection. Now, what they've gone ahead and done here is set this to OX03. So if you think about what that's going to mean, it means we have a 1 and a 1. So these are both set to 1, which means that internal DC to DC is going to be for both the source and the gate. So that's what that means. So what I can do now is write in my hash define and give this a more meaningful name. And I'll show you what I've done. I've done that for all of these command datas as well. I'm not going to go through that on video because I don't want to waste your time, but that's the idea. I went through and I lined this up with what the datasheet was saying, and I gave it a more meaningful name, just like I did with the commands. Before we can write our own init function, we have to give the library a way to actually send data over SPI, because now that we're on the comms layer, that's what we're going to be doing most of the time. So you can see here, they've done a write CMD thing here, and what they're basically doing is bit bashing SPI. So they're putting source clock high, they're putting the chip select low, they're sending data, and then they're putting the chip select back high. So they're sort of bit bashing SPI. These days we have hardware abstraction libraries that will do this for us, and we can send data 1 byte at a time. You'll notice what they're doing here is actually sending data 1 bit at a time. We don't really want to do that. So what I'm going to do is write an abstraction that essentially uses function pointers as a way to give the user a way to register their own SPI send function. And I'll show you what that means. It means we end up with these extra lines here. So if we go from top to bottom, we have 3 dummy functions that do literally nothing at all. So what they do is, this is a dummy transmit, so a dummy SPI data transmit that takes in a byte and does nothing. A dummy CD or DC to change the state from command to data, as you saw in the datasheet, and a dummy chip select pin. So what we can then do is register these function pointers, so BD SPI TX, and that is what our library is actually going to use every time it needs to transmit a byte over SPI. So right now it's registered to this dummy function that does nothing, but what the user can actually do is to generalize this for every hardware platform imaginable. The user can actually write their own SPI transmit function using their hardware abstraction libraries provided to them by their chip manufacturer, whether that's Nordic or STM or Atmega or whatever. And they can then register that using this function here, using a function pointer, and then the library will be using the correct SPI transmit for their hardware platform. Same thing goes for these. These are just GPIO pins, right? So it's going to change depending on your hardware platform. So you can just register your own, and the library will just use that internally. Here's our very own init function. The difference is night and day. This is a lot more descriptive, and you can easily map this to the datasheet. Now, I did do a transmit command and a transmit data. All that does is do our set CD to true, which means it's setting the line high, or set CD false, so it's setting the line low, for transmitting a command or data respectively, and then it uses this SPI TX we talked about. But yeah, this is our new init function. It's the exact same logic as this one over here, but just translated nicely with our hash defines. Am I going to pretend to know what half of these do? The answer is no. All I know is that they work, and I haven't bothered to read into it too much. I know what some of them mean, but the other ones I just haven't bothered to look into, and you don't have to either. That's the beauty of this thing. If you've got manufacturer provided code, you don't necessarily have to understand all of it. Now we want to know how to render the frame buffer to the screen. So this is the thing of interest here, right? Where in the main, we can init the display. How do we render a frame buffer? And that's done here with this pick underscore display underscore GC that takes in this image as a parameter, which is actually the size of a full frame buffer. So this function right here, what does it do? It's got this border flag here, some logic, and then it transmits some cryptic commands, but don't worry, we mapped them, so we'll know what they do. But this is going to be something that we're going to have to keep track of in an internal state. So instead of having these big globals, I might keep a state struct somewhere or something like that. And then we do this. So we write this command, ox13, and then it looks like we loop through the entire frame buffer because that's gate times source. That's, going to be our size divided by 8. So that's the size of our frame buffer. And pick data here is what we're transmitting as part of this thing. And that's going to be transmitting every byte in our frame buffer. And then after that, this formatting is horrible. We call LUTGC and display refresh. So what do those do? We're going to investigate that. Here's our mystery function, and it is so cryptic, it's unimaginable. Here's another thing we're going to have to keep track of in a global state variable. There's some flags here that are getting set all over the place. We're sending a bunch of random commands, and then we're looping through. And this is, LUT stands for lookup table, if you didn't know. We're just using slang. And then it loops through and sends all of these random things. So what are these? Well, these are actually arrays that are kept up here at the top. So these LUTs, what they actually represent is a waveform. I think, to the best of my knowledge, I'm not going to pretend to be an expert on e-paper displays, but to the best of my knowledge, this is an electrical waveform that gets sent through the pixels of the display that actually causes them to physically electronically move and update. And this is why we have to send that to the controller, because the controller could be controlling a number of different panels, and it's up to the panel manufacturer, who is in this case the one who's provided our code, to provide us with the lookup tables that are appropriate for that particular panel. So that's what we have to send to the controller, the lookup table for the electric waveform that it has to generate to update our display for this particular panel. And so that's what we're going to be transmitting. So we're going to have to copy all of these lookup tables into our driver, because that's what the manufacturer provides. If the manufacturer doesn't provide the lookup tables, good luck, buddy. I think you're cooked. So we're going to have to do that, and then we'll look at replicating this logic wherever it was here. I think we can make this a lot nicer, and we'll move this to a global state. There's a GC waveform, which is a full display refresh. So I think with e-papers, you can do a full refresh or a partial refresh. The partial refresh here is DU, and DU, from how I've been using it, it updates a lot faster, but you could potentially get ghosting. So that's the thing you got to worry about. So there's DU updates, which are faster, about like 2 times faster or 3 times faster to update, but you could get ghosting. Or there's GC, which is a full refresh. So these logic essentially look exactly the same, but it just looks like the lookup tables are different. So what I might do is like swap a pointer depending on what refresh you want to do. I'll think about it. I mean, I've already thought about it. I'm pretending to think about it. I've already written the code, obviously, so I know how I would do it. I'm not going to go through it and explain this while I'm writing it. I'm just going to show you the finished product, and I'm going to explain it there because I think that's going to be a lot better. Here's the mining that I did off camera. Over here, we've got an enum for the lookup table type, because remember, we've got 2. We've got a full refresh one and a partial refresh one. I've got an internal state thing that keeps track of, these flags and stuff that this function is setting that were previously just global. So that's just a way for me to organize them a little bit better. And over here is where I've actually done the LUT transmit. Now, essentially what I've done is I've taken this logic here and I've implemented it using state variables, and, I swap the pointers here for the lookup table depending on the type. So, you can say, if we're using this type, we're going to do this one, just so we don't duplicate this across 2 different functions. And of course, the commands actually have LUTC, as the command instead of like OX23 or whatever it is. So hopefully that should be a lot more readable. But yeah, this is essentially just a logic clone of this one that I've formatted a bit nicer. I've done proper hash defines. I've done a global state variable and things like that. And so now what we can do is look at actually transmitting our frame buffer, which was the thing that we were looking at before, right? So we've got the pick, display, whatever function, which was down here. So you can see here, we just do write CMD for the border. That's if we want to do the border. We've got transfer new data or whatever, which is DTM2. That's the same command. And then we transmit the frame buffer, and then we call this. And I've actually included a parameter for if you want to do a full refresh or a partial refresh, and it will do the correct LUT either way. And then we just call a refresh. And yeah, so that's pretty much it. We're ready to put this on a real display. That is super exciting, isn't it? There's one last quirk with this display I need to mention to you guys before we render this on real hardware, and that's that the controller is expecting a frame buffer in portrait orientation, whereas we're addressing it in landscape mode. So what we have to do instead is when we do our set pixel and get pixels, we just have to transpose them. So this is the previous logic in landscape-wise operation. So you can see here we're doing the width times y plus x, which makes sense, and here we're doing x shifted, but we have to change that to height times x plus y and then y shift, just so we transpose that from landscape mode into portrait mode when we're addressing this. Not sure how many of you guys have worked with ST microcontrollers before, but the dev board that I'm demoing on has one. So I'm setting this project up in CubeMX. We're only using SPI1 pretty much. So I've got that set up. We're a transmit only master. We've got 8 bits as our data frame size, and we're sending at 8 megabits per second because the controller only supports 20 or less. In terms of GPIO, we need one for chip select, one for command/data signaling, one for display reset, and one that we're taking in as a busy pin because, you know, sometimes the display can be busy and we want to know about that. But that's pretty much it. It's a pretty simple project. We're pretty much just using SPI. We're here in the main.c file that Cube generated, and here's some of my own code. So I've done the set CD and SPI-TX and a reset display function that just toggles the GPIO pin for a little bit. That is appropriate for my hardware platform because I'm using STM, so I'm going to be using HAL. And you can see down here, we can actually do this register thing. So set CD, and we can give it the function pointer to this custom one that we've specified, and the same thing for SPI-TX. So all we're doing, this is our user code, everything else was generated by STM Cube. We power on the display, init the display, and then we're going to fill the frame buffer with white, draw the bitmap of our smiley face, draw trend.surf, and then draw some vectors, and here we just render the frame buffer again and again and again every 2 seconds. So technically this would be a 1 FPS every 2 seconds. So that would be, I don't know, 1 divided by 2 or something like that, 0.5 frames per second. Pretty high. We're pushing pixels here, guys. So yeah, let's render this on the display. Ignore how messy this setup is. It was thrown together very haphazardly for this video, but what I want you to focus on is this display here and this STM dev board. Now when I flash this code, hopefully we're going to get our frame buffer. So let's try that. Power on, and after 2 seconds we should render our first frame. Boom, there we have it, the smiley, trend.surf. Can you see the little triangle there over the R? That's the triangle. I don't think the square and the other triangle are showing because they're drawing in white when I've set the background color to white. But yeah, you can see there we're actually rendering that frame buffer to the display, which is really sick. And that's how I did, you know, these other two here, set them up. And a great thing about e-paper displays is that they actually retain their image when they're powered off. So I can fully cut the power to this thing and it will retain the image on the screen. Pretty cool, huh? That's it from me, guys. This was an absolute mammoth of a video to put together, and I really hope you enjoyed it. Cheers.